Okay, next up in our review, we're going to go through shapes of molecules, also known as molecular geometry. And for this, we're going to use what's known as VSEPR theory, which I don't know why we call it VSEPR theory, why we pronounce it that way, because to me it looks like VSEPR theory. Anyway, but what VSEPR theory says is that the most stable three-dimensional arrangement of atoms keeps the groups on the central atom. So, central atom, the groups on the central atom as far apart from each other as possible. So as far apart from each other as possible. So with this, when we get that an atom, a central atom is surrounded by two groups, and when I say groups, I actually mean groups, not just bonds, where groups count as, they can be a single atom, it could be a lone pair, or it could be a group of atoms. So, two groups, not bonds, but groups. Then that molecule that's in question is linear, and the bond angle is 180 degrees. So, let me change that. There we go. Linear, and the bond angle is 180 degrees. So an example of this looks like this. We can have HCN, which if we drew the full Lewis structure using what we just learned, or what you were reminded of about common bonding patterns and how to figure out the Lewis structure, we can see that, okay, with this atom, or this molecule has a central atom, and that's a carbon. And so we're looking at the carbon, we're seeing how many groups there are around it. So here it has one that's a nitrogen, and then the other is a hydrogen. So notice that the carbon is connected to a nitrogen through a triple bond, so it's sharing 6 electrons with it. It doesn't matter that we don't count the number of bonds, we count the number of groups. So the carbon that's in we can say that the shape of the carbon atom in this molecule, or the shape of the whole molecule, overall is linear. Okay. So another example that you might be a little more familiar with than hydrogen cyanide is carbon dioxide, right? That good stuff that is just making global warming so much worse. So this central atom is also surrounded by two groups. So this is also linear. Another thing to note is that every carbon that has either 2 double bonds or 1 triple and 1 single bond, like we see in these two examples, every single carbon that has that arrangement is going to be linear. So is linear. Now we can apply this to atoms in larger molecules. So let me pause and draw an example of that. Alright, so here is my example. So the question might be, find all of the atoms in here that have a linear shape. Now this is a big, well, not really very big, but it's a bigger molecule than what we are probably used to seeing at this point. So what we're going to have to do is look at every single atom and see if each atom is surrounded by 2 groups, or if it's surrounded by a different number of groups. Okay, so we're going to start with the hydrogen. Well, the hydrogens, they're only ever surrounded by 1 group, so we don't really, they're definitely not going to be linear. This oxygen, well, okay, we're going to get to that in a minute, but this oxygen is surrounded actually by 4 groups. It's surrounded by, this carbon over here and a hydrogen, but then it also has those 2 lone pairs, so we don't know how to deal with that one yet. So, okay, so then next we have a carbon that is surrounded by 4 groups. So we have a hydrogen, carbon. Well, actually we would count this whole group, but anyway, we can look at what it's directly bonded to. So it's surrounded by 4 groups. So, okay, that's also not linear. What about this carbon? Well, this carbon is connected to one other carbon on one side and then another carbon on the other side. So sure enough, this carbon has 2 groups surrounding it, and this carbon would be linear. Same as this carbon. Then the chlorine, well, that's surrounded by just 4 groups, but 3 of those are lone pairs. So what I want you to get from this is that just like we can classify a molecule overall, if it's a small molecule like one of these two, just as we can classify them as linear, tetrahedral, trigonal planar, trigonal pyramidal, any of those, we can also look at individual atoms in a molecule and classify them based on their shape. And so that's, again, just like thinking about the three-dimensional shape of molecules. All right, so let's go on to another example. When we have an atom that's surrounded by three groups, that atom is going to be trigonal planar. So trigonal planar. And the bond angles, so the bond angles are 120 degrees. So an example of this is H2CO. So this is formaldehyde. Now, every carbon that has one double bond and two single bonds is going to be trigonal planar. So use the wrong color there, is trigonal planar. So an atom that's surrounded by four groups, that's our next like shape in molecular geometry. So an atom that's surrounded by four groups, and all four of those groups are atoms. So I'm going to clarify. So four groups and all four are atoms. So in other words, I'm not talking about lone pairs yet. This will be tetrahedral. And the bond angles are 109.5 degrees. And one thing that I want to point out with this is that it's not flat. So when we look at, for example, CH4, so CH4, it looks, if we just like looked at it on paper, it looks like it's flat, right? But really, it's just because we're like limited to drawing it on paper that it kind of tricks us in that. Really, this molecule, which is called methane, CH4, is tetrahedral, where if you can imagine this shape right here, so this is a tetrahedron, you imagine the carbon that's in the middle, it's kind of like a pyramid. So the carbon that's in the middle, and then the hydrogen there's a hydrogen pointing to each of those three edges. And every carbon that has four single bonds is tetrahedral. Okay, so let's go back and see if we can classify that any more of the atoms in the previous molecule as being either trigonal planar or tetrahedral. Well, okay, so here I'm not seeing anything that's trigonal planar because I don't see anything that has exactly three groups around it. However, I am seeing one that's tetrahedral. I have a carbon right here that's connected to four groups, and so this carbon, we would classify it as being tetrahedral. Okay, still haven't dealt with that oxygen though, and generally what happens when we have like one of the groups being a lone pair. We haven't talked about that yet. Or you've probably talked about it in your previous class, but in our review we haven't talked about it yet. Before we go on to answering that question, so like, what do we call it when we have lone pairs that are involved as one of the groups? A couple of notes about drawing in three dimensions. When we are drawing a three-dimensional tetrahedron on a page, we are going to use wedges and dashes to represent that three-dimensional space. So we're going to use a solid line. So just like a line like that for bonds that are in the plane. And when I say plane, I don't mean like, in the sky. I'm talking about like the plane of the paper. So the plane of the paper. So this is flat, in other words. We are going to use a wedge for representing a bond that is in front of the plane. So a wedge looks like this, and you can think of this as like coming out toward you. So toward you. Then finally, we're going to use a dash. Whoops, I drew it out instead of writing it out. We're going to use a dash for a bond behind the plane. Okay, so that's going away from you. So when we are representing methane, so CH4 in 3 dimensions, well, if we draw it like this, I mean, that's technically correct. That's the Lewis structure, but it gives us a little bit more information and helps kind of remind us that, oh, right, this molecule is tetrahedral if we draw it instead like this. So we have a carbon here. We have 2 lines where that's representing that's flat. So both of the hydrogens and this carbon, we could take a knife and slice through them sideways. So, knife slicing like this. That doesn't look like a knife, but anyway. And then the other 2 hydrogens, one of them is coming out at you. So it's like this hydrogen is sticking out toward you. And this other hydrogen is sticking out away from you. So that's how we represent something that is tetrahedral when we want to be really clear about it being tetrahedral. Now, it gets confusing because, again, if we write this, it means exactly the same thing. But when you see this, this representation, I want you to think in your head, okay, this is what it really looks like with this tetrahedron kind of thing going on. Okay, so let me just write a couple more things here. And that was just so I can have everything clear. So again, the lines that are just solid lines, those are in the plane. The wedge is in front, so coming out at you. And then the dash is behind, so going away from you. Okay, so what about when we have that one of the groups is a lone pair, or maybe even 2 of the groups is a lone pair? Let's look at an example of that. So when nitrogen is attached to 3 atoms and has 1 lone pair, it has a shape of being trigonal pyramidal. So making the shape trigonal pyramidal. So here, notice that I've drawn, well, not drawn, I've stolen it from the internet, a picture of a tetrahedron again. And so just like we put the carbon with the 4 hydrogens in the middle of the tetrahedron, we're going to put the nitrogen with the 3 hydrogens and the lone pair in the middle of the tetrahedron. So here we have the hydrogens that are pointing to the edges, but notice that there's a lone pair that's replaced one of the hydrogens that was on the carbon. So this lone pair is going to distort the overall shape of the molecule. And when we are thinking of the shape of this molecule, we recognize that even though that lone pair is there and it's distorting the shape, when we actually think of the shape of the molecule, what we have to do is just look like that. Yeah? So you can see that it's a lot more flattened out than the regular tetrahedron. So this is what it looks like if we draw it in the Lewis structure. Again, just like with the methane, the CH4, this is called ammonia, drawing the NH3 like this, it's a little bit misleading because it's not really clear about what the 3-dimensional shape is. But when you see this, I want you to think, translate in your minds, okay, this actually looks like this in 3 dimensions. Now, whenever we have an atom that has 4 groups surrounding them, and one of those groups is a lone pair, we're going to get this same shape, this same molecular geometry of trigonal pyramidal. Now, another thing I want to note is that while nitrogen is usually trigonal pyramidal, that's not always the case. So I just wrote nitrogen, not always trigonal pyramidal. So for example, if we have this molecule here, we have this nitrogen, it only has 3 groups surrounding it, right? It has the oxygen, the hydrogen, and then this lone pair. So, that would not be an example of a nitrogen that's trigonal pyramidal, but most of the time it is. Now, again, we call this trigonal pyramidal because even though we have 4 groups around it, so we have the lone pair and then the 3 hydrogens, even though we have the 4 groups, one of those groups is a lone pair, and so we're getting that kind of flattened shape instead of the perfect tetrahedron. Okay. Another example of a different, and this is our final shape or our final type of molecular geometry, is when we have something that has 2 atoms and 2 lone pairs. And this happens with oxygen all the time. So when oxygen is attached to 2 atoms and has 2 lone pairs, that makes the shape bent. Okay, so if we draw what oxygen looks like, let's say water, for example. So in a molecule of water, for example, we draw it like this, and, well, you can't really tell just based on that picture. It kind of looks like it's flat. We could also draw water like this, though. And this shows it a little bit better that it's bent, but it still doesn't get like that full picture of like what it really looks like. So just like we did with the nitrogen and with the carbon in the previous 2 examples, we're going to take the oxygen, we're going to put that in the middle, and we see that there's a hydrogen pointing, well, 2 hydrogens, each pointing to a vertex, I think it's called, of this tetrahedron, and then we have a lone pair that's pointing up to this vertex, and then another lone pair that's pointing over here. But again, when we are considering the overall shape or the overall molecular geometry of the water molecule, we recognize that these lone pairs are here and that they distort the shape, but overall, what we're still doing is figuring out like what the shape is, just taking into account the atoms. So we can see that it has like this kind of bent shape like that. And again, this is not tetrahedral because even though it has 4 groups total, 2 of those groups are lone pairs. Okay, so hopefully your mind is not reeling too far yet. Hopefully this is mostly a review. If not, though, again, please let me know. I have lots of resources that I can share with you. So here is a handy-dandy cheat sheet that is nice for reference. You need to know these, but this is a good cheat sheet. So this goes through the total number of groups. So if we have 2, 3, or 4 groups, that's the first thing that you check. Then you check the number of lone pairs. I would actually kind of just get rid of this number of atoms because that is not going to be helpful when we get into bigger molecules like that example that I just showed you a while back. So you count the total number of groups, the total number of lone pairs, and then from that you can read off the shape around the atom. Now the purpose of all of this is not just to torture chemistry students. It is so that we can think in 3 dimensions, and when we're thinking in 3 dimensions, that helps us in figuring out overall if a molecule is polar or nonpolar, which has huge effects on its intermolecular forces, which has huge effects on everything else. So before we go on to that, though, let me go back to that one example that I showed you, and let's classify the rest of the central atoms in it. So, okay, so we've gotten the carbons, and the chlorine is on the edge, and all of the hydrogens are on the edges, so we don't really need to worry about that. What do you think about the oxygen, though? Well, it has 2 bonds and 2 lone pairs, so 2 groups, well, 4 groups around it, and 2 of those groups are lone pairs. So this would be bent. So to wrap this up, I want to give you a practice problem that's like the one that I just showed you, where you take a big molecule, or a bigger than what you're used to molecule, and figure out what the molecular geometry is around each of the central atoms. Because oftentimes, like you saw, we have more than one central atom. So this is all about getting you to think in 3 dimensions. So let me pause and draw this, and then I'll have you try it out. Okay, so here I just drew 3 different practice problems for you. I would start with the ones on the right because these are the more simple ones where you can classify like the molecular geometry of the whole molecule. And then once you're done with those, I would move on to this, where you are classifying each of the central atoms, so any atom that's not on the edge, you're classifying the molecular geometry or the shape around that specific atom. So go ahead, pause the video, try this out, and then we'll come back together and I will go through the answers. Okay? 3, 2, 1. Okay, so here are the answers. So this would be trigonal planar. We have the central atom has 3 things surrounding it. This one would also be trigonal planar. Even though it's connected through a double bond, it's still only connected to directly to 3 things. Okay, so then this one, I actually want to revise this just slightly, and that is by taking, I had this as a boron, and I wanted to change it to a carbon, because if that were a boron, it would have a positive charge. Anyway, that's not super important. Yeah, okay, so let's start at the top right with this carbon that's connected to the oxygen through a double bond. So this is directly connected to 3 groups, so this would be trigonal planar. Then we have the oxygen right here that has 4 groups. 2 of those groups are atoms and 2 of those groups are lone pairs, so that would be bent. Then we have the nitrogen right here, 4 groups, and 1 of those groups is a lone pair, so that would be trigonal pyramidal. Then both of these carbons are connected to 4 groups, so both of these carbons would be tetrahedral. So in the next video, we'll go through how to tell if a bond is polar, and then also how to tell, at least we'll begin how to tell if a molecule is polar or nonpolar. See you then!